I will introduce the conference. Recording started. Yes. We use the topic and then takes so at least we why I get it to just start. I haven't lecture, but so now before I start, it's working. It's working with arrow keys, right? Yeah. You need a pointer.
I might need a pointer at some point. Yes.
Let's wait for 2 minutes. We stop there. That's it.
Some technical issue.
Hello everyone, welcome to Bangalore Theory Seminar Series. Today we are very excited to have Uddalok Sarkar as our guest speaker. So Uddalok is a PhD student in computer science at IISc Kolkata, where he is advised by Saurav Chakravarti and Kuldeep. So he is interested in distribution testing and formal verification. Today, he has very kindly agreed to give talk on his exciting work, which is titled Self-Reducing Samplers. So let's welcome Uddalok.
Good afternoon, everybody. Thanks for this introduction. So I'm a PhD student at India Statistical Institute, and today I'll be talking about our work on testing self-reducible samplers. This is a joint work with Saurav Chakravarti from India Statistical Institute, Rishinath Bhattacharya from University of Birmingham, Yash Pote and Shayantan Sen from National University of Singapore. So let us begin. So in our group, we have been interested in understanding the correctness of samplers and to design testers for verifying the correctness of samplers. Throughout this talk, we'll be seeing how we are defining the correctness of samplers, what are the interpretation of close to a correctness or far from a correct sampler, and how we dealt with the interactability of testing samplers by using the power of conditional sampling. Because most of the talk will be on testing samplers, let us put some time on understanding what is a sampler. Sampling from distribution itself is very well understood. So it's basically you are given a distribution on some domain set S, and okay, it's fine. Yeah, you are given a distribution on some domain set S, and you are getting samples from that particular distribution, which means basically you are drawing samples from the set following the distribution, which is you are given access to. A sampler is basically a probabilistic program that gives you an access to a class of distributions. And how does it work and how does it look like? Let us see some examples that will clear it up. So here we have a linear extension sampler that takes a partial order set as an input and samples or draws some sample, which is basic, and the samples are basically linear extension of this partial order set. So on the left hand side, I have a partial order set, which is on the set containing elements 1, 2, 3, 4, 5, and the partial orderings are denoted by these black arrows. What the sampler does, when this partial order set is given as input, it basically draws a compatible linear ordering, which is compatible with the partial order set, which is basically the linear extension of this partial order set, and the linear ordering is denoted by the red arrows over there. The sampler head, given this partial order set as an input, it samples one of these possible linear extension out of it. If you change, sorry, I forgot to mention, and how it does it, it follows some underlying distribution while drawing the samples, which is in this case the PS1. As you change the input to a different partial order set, the underlying distribution of the sampler will surely change based on the possible linear extension of that partial order set itself.
Not all linear extensions are equally well.
Yeah, may not be the case, or we might not want all the linear extension to be equally like. It depends on the scenarios. And also, perfect matching sampler, which have been very well understood and well established in theory, given a graph as an input. The sampler basically samples perfect matching of the graph following some underlying distribution. So more examples on CNF sampling, which is very famous in the realm of formal verification, which takes the CNF formula as an input and tries to sample satisfying assignment of this CNF formula following some distribution itself. Now, as you've seen so many different examples of samplers, let us understand why sampler testing itself is a very important kind of thing that we wanted to look into. So most of the systems around us uses some kind of randomness, source of randomness, and the source of the randomness are basically some kind of samplers that we will be looking into. Systems always assumes samplers to be perfectly working or samplers to be reliable. It can completely go wrong or can completely fail if the sampler itself is not working properly or it misbehaves. And how can a sampler misbehave? It can be scenarios that there can be implementation bugs while implementing the sampler itself, or there can be heuristics. So why heuristics is the heuristics is a very important factor in designing samplers, because designing sampler itself is a very hard task. And because, for example, it is known to be sharply hard in for sampling perfect matching from graphs. So therefore, in most of the cases, heuristics are used quite a lot in designing samplers, and we will see some scenarios where like heuristics are kind of inherent to the samplers, and therefore it was kind of our task to certify those heuristics on the fact that whether the heuristics are at all working in a perfect way or it is not working in a perfect way. For example, the MCMC samplers that have been around for quite a lot of time. The MCMC samplers is known to have long convergence guarantees, and often while they are on use, they are mostly stopped prematurely before their convergence. Consider the CNF formula, CNF samplers that I've just talked about. Take the CNF formula as an input and set it sample satisfying assignment. Those kind of samplers use heuristics like random start or random starting or random branching. Language models use heuristics like beam search, nucleus sampling, and even the very basic kind of samplers like binomial sampler, Poisson sampler. These kind of samplers use heuristics like factorial approximation and different kind of underlying approximations. So this is the reason why sampler testing was very important. Suppose consider the fact that we are going to use binomial sampler some point of time, but the samplers that are there in the libraries use heuristics and approximations, and therefore the distribution may completely deviate from the binomial distribution itself. So this is basically the reason that why we were very much interested in designing testers for samplers. And what our task would be, to certify these kind of heuristics, whether the heuristics is good or the heuristics are bad. So this is basically the basic framework of designing testers for samplers. Testers take a sampler as an input. The testers take a sampler as an input and a distribution as an input. The distribution is basically the intended distribution or the design distribution of the sampler. So while the sampler is when developer is going to design a sampler, they are going to design a sampler to follow some particular kind of distribution. That distribution is called the intended distribution or the design distribution. What the tester takes the sampler as an input and the design distribution as an input, and it outputs true if the sampler's distribution are close to the design distribution, or it output false if the sampler's distribution deviates quite a lot from the intended distribution. And the focus of the talk would be to build the testers.
Like the L1 distance.
Yes. So there can be two kind of, as you just pointed out, there can be two kind of distributions or two kind of access to samplers. One is basically unknown distribution, from where I can only get samples, but nothing else I can do. That is called an unknown distribution or a black box access to a sampler. On the other hand, I have a sampler or a distribution for which I not only can draw samples, but I can also query its probability in very easily, like in one time. And what I want to do is we want to estimate the distance between these two distributions, the unknown distribution and the known distribution. Yeah, this coming. So
you say evaluate you mean what is, so assuming like finite support distribution, and evaluate you means what is U of X?
U of X, yeah. So given any X, you can evaluate U of X in a constant time. These kind of distributions are kind of known distributions. I will be calling it known distribution. So in this one, we have taken total variation distance into account. The total variation distance is defined by summation of pi minus ui, where pi is greater than ui. And the reason behind using total variation distance, I have a very nice explanation of why total variation distance was the matter of interest to us, but that would be a bit orthogonal to the talk. Therefore, I will be happy to talk about it after the talk maybe. And the distribution P will be called epsilon close in our case if the distance, total variation distance between P and U is less than epsilon, in which case the P will belong to this green ball centered at U of radius epsilon. The distribution P will be called eta far from the distribution U if the total variation distance is greater than eta, in which case P will belong to this orange region, which is basically out of the ball centered at U and radius eta. So these two terms will be using quite a lot throughout this talk. So therefore, I'm just defining it right now. So moving forward, the entire problem that we want to solve while designing testing for samplers boils down to this problem in theory. Um, we have a domain to be an n-dimensional hypercube that is 0, 1 to the power n, but that can be generalized very easily. So given that domain in our hand, let us define the problem. We have an unknown distribution P on the n-dimensional hypercube. We have a known discrete distribution U on the same n-dimensional hypercube. We have a tolerance and an intolerance parameter, epsilon eta, and a confidence parameter delta. All of them are between 0 and 1. With high probability, we want to output reject if the total variation distance is greater than eta. And with high probability, we'll be accepting if the total variation distance is less than epsilon. So you just want to decide between these two factors, whether total variation distance is greater than eta or it is less than epsilon. In this work, we are kind of addressing a rather harder version of this problem, in which case we have the same known and unknown distribution, the tolerance and the confidence parameter, but no intolerance parameter. And we want to output a epsilon additive estimate of the total variation distance with high probability. In this case, we are no longer deciding, but we are directly estimating the total variation distance. And given the estimate, we can surely always decide between these two factors. Now, moving forward, solving this problem by only getting samples from the unknown distribution requires exponentially many samples. So this is the main bottleneck in designing testers. If you need exponentially many samples, it would be rather impossible to design any kind of testers that will practically work for any kind of samplers. This is the main bottleneck that we have. But still,
So what's the dependence on epsilon?
so the dependence on epsilon I haven't shown here, but it is kind of 1 by epsilon. You can the lower one that we have is kind of 1 by epsilon. Yeah, I mean, delta people do not show usually in the lower bound for taking it a constant, but yeah.
Epsilon square.
The lower bound is still like there is this gap 1 by epsilon, 1 by epsilon.
If it is not a
Uh-huh.
support of size n,
Uh-huh.
then it is n by epsilon square.
Yeah.
Log, yeah, it's the even log 1 over delta, there is some square root by point bias, right? So has a 1 over epsilon.
Yeah. No, I mean that would be more or less similar. I think if that is 1 by epsilon square, what there. So point bias. It's 1 by epsilon square, right? Yeah. Right. Yeah.
I mean, this bottleneck holds when you know you explicitly, that is, you know the, like, let's say the density,
Exactly. Yeah.
and still, and the P is only sample access.
Yeah.
So if you don't divide it by n, you can estimate the P itself of fluid.
Right.
Not even distance between P and U, you know P itself of P.
Yeah. That like it's like learning the distribution. So yeah. Yeah. So let's move forward. Yeah. Even though there have been these bottlenecks, but still there have been quite a lot of working on designing testers itself. The main crux behind all these testings, the testers, is this kind of arguments that for most of the samplers in practice, we can have a special kind of access to the samplers. So I'll be sure soon revealing what are these special kind of accesses. Since long, like this has been a real interesting thing to look into, that even though we have one kind of access to the sampler, which is a black box access, in which we can only draw samples. On the other hand side, we have a white box access, for which not only we can draw samples, but we can also query its probability. there have been since long there have been an interesting question whether there can exist something in between. Whether there can exist some gray box kind of access, which is much more powerful than black box access, but surely quite less powerful than white box access. So what we do in this work, we come up with a tester. We call it QPro, that provides testing framework for quite a lot of broad class of samplers. For example, CNF-sampler, language models, linear extensions, and many more. And for QPro, it is a sample-based tester that uses some conditional sampling access to the sampler. This conditional sampling is basically the special kind of access that I was talking about. And let us now look into what are these conditional sampling access and how does it look like. So let us again recall this linear extension sampler that I defined long back here. So, and suppose on the right hand side is the distribution of the sampler when this poset is given as an input to the sampler. As soon as I introduce this edge from 3 to 2, these two samples cease to appear in the output of the sampler. And this is the current distribution of this sampler that we get. This is basically the conditional distribution conditioned on these two assignments these two linear extensions sigma 3 and sigma 4. And this is how you can get conditional kind of sampling access in the case of linear extension sampler. So now let us look into more detail of conditional sampling access, and we'll see that this kind of access, to get this kind of access, the only thing that we need to do is to design some kind of oracles that will give us access to this kind of conditional distribution. So the first kind of oracle, or the very general kind of oracle, is the conditional sampling oracle that takes the sampler as an input and a conditioning query as an input. The conditioning query is basically a subset of the domain itself. And what does the oracle does? The oracle forces the sampler to output some point from this conditioning query, following the distribution, which is proportional to its mass to its probability value in the original distribution. So by this, we can get an access to a conditional distribution. But the main problem behind this kind of oracle is very hard to realize in practice. Yes. The S is basically a subset of the domain. So you see, when I was talking about partial order set, that is basically a subset of the entire n-dimensional hypercube, right? So that is kind of the S here. S is the domain of the distribution right now. So you can consider S to be the domain of the distribution P. And the conditioning query.
Chop off the domain and say condition in the part like sample lies in S. What is the problem?
Yeah.
So the K is size of S.
No, K is much more less than the size of S. So if K is the size of S, then obviously you will not getting any power, right? I mean, K surely you can make the size of S, but if K is of size S, then this oracle is not doing anything, right? It is again giving you access to the entire probability distribution.
S is the support of the distribution.
Support of the distribution.
This is the support. You should get an element based on the conditional distribution.
Yeah.
No, not this. So think of S as 0, 1, N. It's full to full.
Yeah.
So you just select a subset of elements in your support, K of them. And you just get a conditional probability distribution.
So then cardinality of S is K.
No. I mean, it's some subset.
Some subset of.
This is not like 0, 1, N is not the full support. S is the support.
So
I mean, S is entire power to be given.
Right. But let's say you pick S to be some subset of.
Yes.
Now you are getting sampling only from that support S.
Yeah.
No, you are getting from sigma
Support
to
by
sigma.
definition is all points where P is 0, non-zero. Or bad notation. Peculiar notation. So, I guess all the intent here is to highlight that the distribution might not be defined on all the entire hypercube. Like S is all the binary vectors where the probability is non-zero.
Exactly.
It is literally the support of T or T. And so you pick some subset of the support, you will get these conditional probability. Like you will get a draw.
H could be nothing but n by 2.
Yeah.
K could be only 5.
S is fixed. You don't get to. It's fixed based on
K is the non-zero. K is the
No.
subset.
Also,
What you were thinking of S before, that is actually sigma 1 to sigma.
So maybe for here in this example, the S is of size 8, K is only of size 4. So S can be as long as 2 to the power ls.
taking what as input.
The oracle is taking the sampler as an input, you can say that it is built on the top of the sampler.
Sigma K and it is just giving conditional distribution.
Yeah.
so what happens is sampling oracle just return some number. If it is sigma to sigma k, it returns, otherwise it will not return. It will just continue doing it.
Then you will print equal number of samples.
I didn't get it. So in sampling oracle, the implementation is bad, but each time you take a number, if the number is within sigma 1 to sigma k, it will return. Otherwise, it will continue to sample.
Oh, then this rejection sampling kind of thing will go on forever, no? If you're not getting any power, in that case, you'll not be getting any power. So if like the question that you had is if K is equal to S, then also you're not getting any power. It's like you are getting samples from the entire distribution itself. We always want to restrict the support size if something. Yeah. No.
Yes, if you are.
Yeah. So you can always think the sampler to be a class of distribution that will first you fix the S, give that as an input to the sampler, and then you will get access to the samples from S. That's why like when I started, I told that sampler is a class program that you access to class of distribution. Not only one distribution, it's a class of distribution. Right. Yeah. So so in general, in practice, implementing this conditional sampling oracle is quite hard and it's not possible. But what you have looked into is if we can restrict the conditioning query to a size of 2, then it is possible to design this kind of oracles for some particular kind of samplers like CNF-sampler. So let us again jump back into the previous works that was previously done on the testers. The first work started with Barbary. It was kind of designed on the basis of pair conditioning sampling oracle that I just talked about, and it was designed for CNF samplers. The distance measures that they used or the problem they actually tried to solve, in that case, they considered either the distribution to be L infinity close or it is far in total variation distance, which is an easier version of the problem that you want to solve. You want to solve whether it is close in total variation distance or it is far in total variation distance itself. So the symmetric in both close and farness distance. It is a bit weaker version than the problem that we actually end up solving. So the second is TIC. It was designed for probabilistic circuits for which you can get white box kind of sampling access. And in that case, they did it for the distance measures total variation distance, both cases. Flash was designed for horn samplers that again use the pair conditional sampling oracle and use the distance measure of L infinity close versus total variation distance far. So this was the previous works that was done in the realm of designing testers for samplers.
Conditional samples can mimic.
No. Black box sampler is not stronger. I mean, it's a weaker, right? I mean, strong white box sampling is stronger. Black box, yeah.
White box, how do you get white box?
You take like sigma into the entire support.
Then you are still getting a sample, you are not getting the
Yeah.
Even here,
Here you
you
are
are
getting
getting
the actual sample.
In probabilistic circuits, we can have evaluate the probabilities actually. So in probabilistic circuit, maybe I'll give a very generic example of language models. The language models are kind of probabilistic circuits, right? And always, if you have the weights, you can evaluate its probability at the end of the day once you have the sample. So given the sample, you
This
uh, uh,
additional variable defined.
Huh.
Are you just getting sample or?
Yeah, yeah. No. It's just getting samples. No.
So then this need not be weaker than your whiteboard sample. You said earlier it is in between
Okay.
black box and white box.
Right. So in white box, we can evaluate the probability, right? Here we cannot able to evaluate the probabilities. But what we can surely do in black box, we are getting only the samples. Here we can do some conditioning kind of thing. We can specify that give me samples from only this subset. And this is that's why it is kind of stronger than black box, but surely it is weaker than the white box.
There you just compute those numbers, the ratios.
Yeah, but if you take the sample complexity, it's not like rule of one, one, two.
Yeah.
White box will give you conditional
White box in O of 1 will give you T sigma 1.
T sigma, just
Yeah.
T sigma.
And then you also O of 1 you get T sigma 2.
Right.
And then you do this.
Yeah, this is fine, but any conditioning, what if the conditioning set is of very?
Okay. Yeah. But K, then you order K. Just like you do N. Support size can be given.
So I was trying to see if there is a particular value of S where this will correspond to white box.
So this will correspond to black box, white box. No, it's not possible.
This will correspond to black box very easily.
Yeah.
You just do it.
We have to be the entire to it. But white box is not possible. The best you can do is pair conditioning. You take 2 points and then you can try to estimate the bias. So ultimately, at the end of the day, you will have to toss at least 1 coin. So that is you have to do. It's not white box. So yes.
Have some explanation for this.
Have some.
Why are the metrics for single values?
Right. So because if two distributions are infinitely close, you can surely always say that they are close in total variation distance, but not the other way around. So therefore, therefore it is a weaker version of the problem where we want to ask if the two distributions are close in total variation distance or it is far in total variation distance. If we have solved this problem, that if the two distributions are close in any infinity distance or it is far in total variation distance, we could have solved the other problem, right?
Strongest.
Yeah, it is a weaker version of the problem, right? No. If it is L infinity close, then you can say it is DTP close.
Matrix and distribution, probability distribution go reverse than the vector.
One versus again.
Yeah, we switch. In vectors higher the norm, like the smaller the value in probability distribution is the difference. L1 was the sum of probability distribution. L infinity is the signal of. And that's why we use script like that. Script L was the vector.
Yeah, does this answer the question? Okay. So moving forward, let us see some time to understand how this pair conditional sampling oracle is implemented in practice, or how does it look like. So I'll be showing you an example on this CNF-samplers domain that was actually been implemented in the first work of Burberry. So it takes a CNF formula as an input, and the conditioning query are basically two satisfying assignment of the CNF formula. What we want to do, we want to do conditioning on only these 2 points or only these 2 satisfying assignments. And therefore, we in the output of our sampler, we only want either 010 or 101, right? And we don't want 011 and 111 on the output, which is also a kind of satisfying assignment of this CNF formula. So we are kind of want to condition on only these two satisfying assignments. How this can be done in the realm of CNF formulas, you can only do an AND operation. So what you will end up with a new CNF formula, which looks like this: phi and either sigma 1 or sigma 2. This is the kind of CNF formula you can generate and give this as an input to the CNF formula. And at the end of the day, you will get us conditioning access to this to the distribution of this CNF sampler. But now, if we want to realize, or we want to move realize this pair conditioning sampling oracle in the realm of graphs, let us see how it looks like. So again, let us get back to the realm of linear extension sampler, where we have the partial order set, and we want to do conditioning query on two linear extensions. So one possible linear extension is 1 is greater than 4 is greater than 3 is greater than 2, and another is 1 is greater than 2 is greater than 3 is greater than 4. So, and on the output, we only want these two linear extension as an output of the sampler. So you want to condition on only these two linear extensions. But at the end of the day, it is not possible to do this kind of conditioning in partial order set for partial order set. And at the end of the day, we will end up sampling some buggy samples, which we don't want as an output, of the sampler. So these samples will be calling a buggy samples. And why at all this is going to be the case? Because whenever we are going to do any OR operation between two linear extensions, at the end of the day, I'll be getting this particular partial order set as an output. And because I'm not getting any new information apart from this parent partial order set, I'm not able to do any kind of conditioning at the end of the day, and I'll be producing samples which are not in the conditioning query.
So if there was a graph
Yeah.
which exactly represented those two
Right.
conditions,
Exactly.
then
Only, yeah. But it is not possible to design this kind of graphs always. Yeah. Yeah.
Even
Exactly. So at the end of the day, you will not be getting any partial order set. So in that case, if you are not getting any partial order set, you cannot use the linear extension sampler at all. You will have to use something other. That is the main problem on using pair conditional sampling oracle. So basically, the story so far goes like this. We don't know how to do test in the black box sampling model. For general conditional sampling oracle, I just told you that it is hard to realize in practice. For pair conditional sampling oracle, I've just given you an example for structured distribution, how it does not work for graph samples, right? Therefore, we used in this work a different kind of sampling oracle, which we call a subcube conditional sampling oracle. And for this kind of sampling oracle, quite a lot of samplers can be tested. Let us see how this subcube conditional sampling oracle look like. So in subcube conditional sampling oracle, we are not the conditioning query looks pretty much different here. Recall that we are working on this n-dimensional hypercube, and now we are not conditioning on any arbitrary 2 points in the conditioning query. What we'll do, we'll condition some dimensions of the cube. We'll be conditioning a subcube, rather say. So the subcube here looks like the dimension k. So we'll be conditioning the first k dimensions of the subcube and giving this as an input to the oracle, subcond oracle. Subcond oracle will produce some satisfying assignment for which the first k dimensions has already been fixed. Now you see this gives us access to a conditional distribution conditioned on the first k dimensions. For an example, this is kind of on the 2-dimensional hypercube. We are fixing the first dimension to 1, and therefore we are getting access to a distribution for which the first dimension is set to 1. This is the main theorem of our work that takes the unknown discrete distribution and assumes a subconditional access to the unknown discrete distribution. We have a known discrete distribution on the same n-dimensional hypercube, a tolerance and a confidence parameter, and we want to output additive estimate of the total variation distance between the unknown distribution and the known distribution. And to do that, we needed only order n square by epsilon to the power 4 many queries to the subconditional. And where does our algorithm stands as compared to others? The previous works only took order n by epsilon square many samples. In our case, we are on the bad side, like we are taking order n square by epsilon to the power 4 many samples. But what we gain is the fact that we are providing some testing framework for a broader class of samplers that also includes the samplers that they started to test for. And the distance measure is also improved. The distance measure that we kind of address here is symmetric, and what we do is DTV close versus DTV first form. This that we gain with at the cost of sample complexity. So let us see briefly see how our algorithm works. So before going further, I'll be using these two terms quite a lot. One is additive estimate, another is multiplicative estimate. I think most of you know what are these, but still for the completion, I'm telling once more. An estimate is called an additive estimate of a statistic if it is within the range of theta minus epsilon and theta plus epsilon, and it is called epsilon multiplicative estimate if the estimator is within 1 minus epsilon into theta and 1 plus epsilon into theta. And at the end of the day, we are going to estimate the epsilon additive estimate of the total variation distance. So let us see how our algorithm works on the very brief overview. So the first idea is have like this thing maps of 0, 1 minus ux by px is a good estimate of the total variation distance between p and d. So had it been the case that we get so therefore we could have drawn only 1 by epsilon square many samples from the distribution p, and by doing an average we could have gone to a good estimate of the total variation distance. But the main problem here is the fact that we don't know p of sigma. For any sigma, we don't know p of sigma. This is the main problem. We cannot evaluate the probability of the sample. We don't know. But what we can really do is we can estimate all this, all the probability values.
Why not symmetric? Look at the symmetric one. Then
Symmetric version of the.
then you will need.
Yeah, I mean, in that case, I will be getting samples from you. So that would be even a problem. So that will not work that again. So that will issues.
P of x is.
Yeah. But in that case, what could have happened? So I might be that possible. I mean, maybe I'll go over it after the talk. Okay, and that will be. I can show you that that is not. That will surely not work. But this will work. That is for sure. Yeah. So, but we can estimate the px values. Is it sub-1? So basically, what we do. The second idea is if we can get a epsilon multiplicative estimate of these px values, we could have gotten a epsilon additive estimate of the total variation distance that we can show. And therefore, what we'll be doing at the end of the day, we'll be estimating all these px values within some epsilon multiplicative estimates. So let us see how these epsilon multiplicative estimates of the px values can be obtained. So this slide looks a bit jumbled up. Let me go over one by one, and then I think then it will be much more clear to you. So because there is an n-dimensional hypercube, all the samples we have is basically n-dimensional vector. And by Bayesian law, you can consider the n-dimensional probability of sigma to be a product of p of sigma 1, p of sigma 1, sigma to given sigma 1, and at the end of the p of sigma 1, sigma 2, sigma given the sigma 1, sigma 2, and sigma n minus 1. So all these n terms will be called conditional marginals because we will be conditioning on up to I-1 dimensions, and we will be seeing the marginal on the ith dimension. So all these terms are called conditional marginals. And at the end of the day, what we'll be doing, we will be estimating all these conditional marginals using the subcon oracle. To do this, note that this kind of conditional marginals can be accessed via subcon oracle, because I have just shown you how the subcon oracle looks like, and with the power of subcon oracle, I'll be getting access to this kind of conditional marginals. So how I will be doing it? I'll be drawing samples of order n by epsilon square many times to estimate each of these conditional marginals one by one. And at the end of the day, I'll be producing all these n conditional marginals. And I can show that given the fact that we have drawn n by epsilon square many samples, all these estimates will be of order epsilon by square root n multiplicative estimates. And when I am producing all of them, the estimate that I get is basically order epsilon multiplicative estimate of the P sigma.
And how do you sum? What is the subcube query to get, let's say, P sigma 1?
Yeah, P sigma 1, we don't need any subcube queries. So it is like, just give me samples. I'll be looking into the first dimension only. So I'm agnostic about the rest of the dimensions. Yeah.
Oh, so it not only okay, fine.
So whenever we are going to do this, I'll be the condition is my
Sigma
sigma 1, and then we get access to sigma 1, sigma 2. I'll be looking into sigma 2.
One question.
I can, yeah. P, so right. So P I'll not need here. I mean I'll be needing, but on expectation, the thing will be at the end of the day, on expectation, it only required n by epsilon square. So you're right that there will be an n by P epsilon square, but because I'll be sampling before I am estimating the probabilities, I'll also be sampling it from the distribution, right? So before, like, even though we are estimating the samples, probabilities of the samples, where are we getting the samples from? We are getting it from the P itself, right? So at the end of the day, on expectation, we don't require so many samples. We only require n by epsilon square many samples. So yeah, moving forward, yeah. So at the end of the day, we'll be requiring n square by epsilon square many samples for each of the 1 by epsilon square samples that we already sampled previously from distribution P, and therefore the total sample complexity boils down to n square by epsilon to the power 4. This is the basic overview of how our algorithm looks like. We use our algorithm to test or to certify some linear extension samplers. So all the linear extension samplers that we have are kind of CNF sampler based linear extension samplers. Yeah, I'll go over it at the end of the, in the conclusions here. Huh?
Courier font like scares me into thinking some program Python code will suddenly pop up.
So yeah. So this so essentially our linear extension sampler takes the partial order set as an input. It converts the posets to CNF, uses CNF sampler to generate some samples of Boolean strings, and later on converts the Boolean strings to linear extensions. And this is how the linear extension samplers look like in our case. And we used 3 linear extension samplers. We not use, basically we are going to certify these 3 linear extension samplers using our tester. So this is kind of the result that we had. So before going to the result, let us go over some known facts that we already knew beforehand about these samplers. So LXT quick sampler are known to have a good amount of heuristics, and then they don't give any kind of theoretical guarantees. Whereas LXT STS is known to have certain theoretical guarantees. And LXT CMS gen was designed on the top of a tester. Therefore, it is well known that it kind of is able to fool the testers itself. So this is kind of this is the known facts about these 3 kind of samplers that we had previously. And now let us jump back to the results that we got. So on the x-axis, we have it is the dimension of the hypercube that I was talking about. The hypercube dimensions are again based on the poset benchmark, partial order set benchmarks that we had. On the y-axis, it is the estimated total variation distance from the uniform distribution. So all the samplers were previously designed to follow some uniform distribution, but then they use heuristics, and therefore their distribution goes deviates from the uniform distribution. And this is the y-axis basically shows the estimated total variation distance from uniform distribution itself. The blue is basically the elastic wave sampler, which is usually was known to use heuristics heavily, and therefore, as the dimension increases, its estimated total variation distance increases quite a lot. Whereas for LXTSTS, whether we knew it has some certain guarantees, the distance doesn't increase much. But for LXT-CMSGen, that was designed on the top of a known tester, actually fails in front of our tester, and it shows its true colors that it's quite a lot of distance from the uniform distribution. So yeah, this is kind of the results that we had is basically aligned with the. It's not fixed number of samples. The samples that required by the cube probe is the upper bound of the samples that we got. To finish up, this is particularly the very first practical framework that use subcon Oracle access to the samplers. And because most of the samplers in current worlds give some kind of subcon kind of access, therefore our tester can provide sampling testing frameworks for most of these kind of samplers. And certifying a sampler not only validates the quality, but also paves the way that in which case you also come up with new samplers that will have certificates from the testers that we design. So it's at the end of the day, we need to design samplers, right? And the better the samplers will work, the better for the systems. And what we do is we provide our testers to provide some kind of certificates to this kind of samplers. And I'd like to finish up with this future work that we had. So the current lower bound that you were talking about is still like the bounds are still open. There is a polynomial gap between the lower bound and the upper bound that we have. And because most of the real world dimensions, high dimensions, are not that dense, they are sparse, and therefore there must be some instance optimal kind of way to test the samplers or test the distributions that would give us an instance optimal testing results that might not need this much of samples. And at the end of the day, it is always open to how to involve more and more testing frameworks for more and more general kind of samplers. So and finally, I'd like to end up with this beautiful spectrum that we had. Sorry for the keywords popping in the middle. The spectrum looks like this. On the left hand side, we have the weaker models, the black box models, which was easy to realize and had higher sample complexity in the realm of testing. On the right hand side, we had stronger models like white box models, which is hard to realize, but it's very easy to design testing frameworks if we had the white box models. And this is kind of the ordering of the models, conditional models that we had, which one is weaker and which one is stronger than the other one. But we still don't know if these two things are comparable. There are still some dots remain that we need to connect to finally infer whether subcube conditional is powerful than pair conditional model or it is weaker. And yeah, this is the link to our paper and report. Please give it a try. Thank you. Yeah, any questions?
Constraint version study, like essentially you are forcing these hyperplanes, and like the subcube is like very component wise constraint. Like one could think of like x1 plus x3 is x1 plus x2 plus x5 is at most Yeah, I have these three type.
No, this kind of things has not been studied.
Not just like using access parallel,
No.
more complicated.
But this is actually kind of the thing that we are kind of thinking of looking into on if we have this kind of linear constraints, and if conditioning can be done on that. Yeah, that might be very interesting to look into actually.
You sample some X or some sigma from a distribution and you want to estimate the probability of that from the sampler, and for that you use these n square by epsilon square
Yeah,
samples
yeah.
by doing this. And so that n square by epsilon square samples would be required to estimate kind of the probability for any arbitrary X.
For any arbitrary.
Yeah, just wondering here, because we have this information that this X itself is sampled from this distribution.
Yeah, exactly.
Kind of use that to improve this.
So actually, what you just said, n square by epsilon square will not be the number of samples that is required to get an estimate for any arbitrary x. It is for the sampled x only. So what Nisha just said, for any arbitrary x, at the end of the day, you will require n square by x epsilon square by the samples. But because we know that x is sampled from P itself, therefore we can say that on expectation, the number of samples that we require is n square by epsilon square. So that is exactly the optimal one that we had right now. So I think I did not answer your question about if it would have been sampled from you, what would have happened. So, yeah, if it is, yeah, that is the question answer actually. If it is sampled from you, it has not been able to say, get a good estimate within that samples.
This pure bound is like what kind of machinery is used to prove this?
Oh, so this lower bound used Gauss principle, like it was using Gauss principle. Yeah. So this lower bound doesn't come from the subgroup conditioning that we did actually, but it was a rather different kind of conditioning that I did not introduce here. That is an interval kind of conditioning. So you query on some intervals of the domain and get samples from that. So basically, what like our this model basically boils down to that by a particular kind of interval conditioning sample or other. It can show that the lower bound follows here also. Yeah, so I mean, yeah, epsilon they have not introduced any lower bound in this work for sure. Yeah.
It is into the pool.
Right.
For some kind of- what is the kind of reading?
Okay. For marginal at ith bit, what kind of query that will? Okay. So in our case, so if we only need the marginal, we don't need to do any kind of conditioning query, right? We'll just ask for a sample. You'll see the ith bit. So this is kind of a projection. Yeah, condition on first I minus one bits. No, so it's like you fix some first I minus one bits, right? To something like that depends on the sample itself. You give that as a conditioning query to the oracle itself, and then look for the ith bit.
Specifically for fiction instruments of alignments.
Yeah. This is the conditioning query that we do.
More questions.
Thank you.
From CSL.
Thanks.